So we're going to go ahead and start it with average value and mean value theorem. And I'm going to, as always, start with a little bit of a review so that you get the background information in case you didn't quite understand in class. So we start here with the temperature in degrees Fahrenheit given by this function. We agreed in class that this function is not a rate, it's an amount. It's giving you the degrees Fahrenheit at a certain time, t, in the interval 0 to 24. We went ahead and sketched a function, and I already have it here for us, where you'll notice we start at 70 and the highest temperature is 90, and then we end back down at 70 after 24 hours. And so the question is, at what rate is the temperature increasing when it is 6 a.m.? You'll notice 6 a.m. is located, probably the middle is around 12. So 6 a.m. is going to be somewhere here. And you can tell that the temperature is increasing, so I expect to get a positive answer when they ask me about the rate. We discussed in class that 6 a.m. is an instant. It didn't tell us the first 6 hours or between midnight and 6 a.m. It just said 6 a.m., which means an instantaneous rate of change. Instantaneous rate of change, of course, would mean the derivative. So we're going to go ahead and take the derivative of this given function at 6. And we're going to get an answer. In class, I showed you a little bit of a shortcut to have the calculator do it for you. I have here my graphing calculator. I've already typed my function. I'm going to just go to the home screen, clear everything up. Taking the derivative is a math 8 function. And I'm going to go ahead and take that at x. Now, I've already typed the function into y1. So instead of retyping it, I can just use vars, y vars, this function, y1. Is going to paste it for me so I don't have to retype it, just a little bit of a time saver. And I want it at 6 a.m. and I'll press enter and it's going to give me an answer. So this is the rate at which my temperature is changing. So I believe that is 2.16, and I cannot remember exactly what that number was, so I'm going to have to go back. 2617, so about 8, 2618. And the units, because it is a rate, we're measuring this in degrees Fahrenheit. And the time is in hours, so it's going to be degrees Fahrenheit per hour. Moving on, they ask us for the average rate in the temperature from 0 to 6. In this case, they actually use the word average in rate of change. And they give us an interval right here, 0 to 6. So in this case, we're actually going to need to do the formula for average rate of change, which is change in y over change in x. In this case, it's change in f at 6 minus f of 0 divided by 6 minus 0. I already know the temperature at 0, but in case you didn't and you wanted to use your graphing calculator to give you that information, especially at 6, here's my table. You guys can access your table by second table set, and I'm going to go ahead and tell it to start at 0, increasing by units of 1, and that will take me to my table. You'll see at 0 it's 70, and over here at 6 it's 80. So we end up with 80 degrees minus 70 degrees over 6. And that is going to be 10 divided by 6, which is 1.666. So if we round, about 1.6 repeating. And we're going to use our units. This is a rate, again, temperature by time. Temperature by time. So it'll be degrees Fahrenheit per hour. That's not up, that's degrees. Moving on, again, average rate of change, this time from 0 to 24. As you can expect, since the temperature at the beginning and the temperature at the end are the same, you end up with 0. F of 24 minus f of 0 divided by 24. And that would be 70 minus 70. Now I already know that it's going to be 70, but in case you didn't, you could easily go to your graphing calculator. And I'm not going to scroll all the way to 24. I'm just going to ask the table to go to 24 real quick for me. Oops, second table. Okay, and there's 24 is 70. So in case you didn't already know that, there it is. So we end up getting 0 degrees Fahrenheit per hour. Okay, next question, and this is the big one, is find the average temperature from 0 to 24. Now this is not a rate, this is literally the average temperature in that 24-hour period. In class I asked you to just kind of guess based on this picture. And you can tell that, I mean, the lowest is 70, the highest is 90, so probably around 6 a.m. I'm guessing it's gonna be 80 degrees. And I would guess, just because 80 is right in the middle of 70 and 90, that's gonna be the average. So I'm gonna guess that 80 degrees is the average. 80 degrees Fahrenheit is the average. Now it's not a rate, it's just a temperature. But that's the question they're asking us. Now this is a guess, but we need to make sure we come up with an algebraic way of doing this. The second thing is, at what time during the day is the temperature the same as the average temperature? I already guessed that it was about 6 a.m. because I guessed that it was 60. And over here, when we found the temperature at 6, we knew it was 80. So probably around 6 a.m. I would say. And then again at 6 p.m. I'm guessing those are the two times where the temperature equals the actual average. These two questions are the ones that the average value and the mean value theorem are going to be focused on. Average value, as you already probably guessed, is going to mean the average value of the function. In this case, the function is giving temperature, so the average value of that function would be the average temperature. And that's the first thing we're going to do. We're going to generate a formula for doing average value. The second thing we're going to do is connect the mean value theorem to that and what it means. Now the mean value theorem actually is going to allow us to answer question F, which says at what time during the day was the temperature the same as the average temperature. So mean value theorem is really going to say the following. Once you determine your average temperature, it makes sense that your function has to equal that average temperature at some time, at least once. It wouldn't make sense that the average temperature happened at 80 and then the function never actually went to 80. So the mean value theorem is kind of intuitive that way, because once you know your average, your function must take on that value at some point. And the mean value theorem says that that's true. That's basically what it says. Your average value must equal the value of the function at some point, at least once. And that's what we're going to go ahead and do, is prove that the mean value theorem. We're going to state the mean value theorem. We're going to use it to help us find where those places are happening. So let's move on to average value. This is going to be a little bit of a proof, and then it's going to give us a formula for finding average value. Before I start, I'm going to need a little bit of a picture and just kind of a setup. So I'm going to go ahead and call this function f. Sorry about the crooked axis. I'm going to call this f of x. And we're just going to go ahead and start at a, and then we're going to go to b, and I'm just drawing some arbitrary function, not anything special. So here's a, here's b. And our goal is to find the average value of this function. It's called f, so it's generic. And so one of the ways that we can do that is we can draw rectangles, just like we did before for Riemann sums. And basically the height of those rectangles are represented by the y values on that function. Now, we don't want to, when we're doing the average, when you were probably in early middle school or grade school, you learned that the word average, to find an average, meant that you had to add up some numbers, whatever you were averaging, and divide it by the number of things you were adding. So we're going to apply the same concept, and so we're going to think of the y values of this function as rectangles. So the average height of those rectangles, that's what we're in search of. It's the same thing as thinking of the average y values. And I'm just going to remind you that the width of these rectangles is going to be delta x. Keep in mind that we're not going to take 4 rectangles, because ultimately we want to be able to do is add up every single y value in this interval. So really we want an infinite number of rectangles, and as we go to an infinite number of rectangles, this delta x shrinks to a very small amount, essentially approaching 0. If you recall, delta x was given by subtracting the interval, the width of the interval, dividing by the number of rectangles. Okay? I'm going to do a little algebraic manipulation here, and you're going to understand why I need it later, but I'm just going to set it up now. If I go ahead and multiply both sides of this equation by 1 over the quantity b minus a. This is legal if I do it to both sides. It reduces here, and it leaves me with delta x over b minus a will equal 1 over n. Okay? And so I'm just going to leave it that here for now. Kind of box it in. And we're going to use this later on in our proof. So let me go ahead and draw a line here. Okay. So average value, how do you find it? Well, just like I said before, you want to add up all the numbers and divide by the number of numbers you have. In this case, the numbers are represented by y values or by the heights of the rectangle. So we want to go ahead and add up all those y values. And just say we start with f of x plus 1, f of x sub 1, which means the first y value, plus the next y value, plus the next one. And you can see that, I mean, it can go on forever because it depends on how many you have. Just going to put n for now. Okay. All right. And what we want to go ahead and do is divide that by the number of rectangles, which in this case is n. Cool. Moving on. This is kind of a long notation with all this plus, 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 plus. So we've already done this before. The shortcut to plus, plus, plus is to use that sigma notation, summation notation. So I'm going to try really hard to make it look. Oh, that's pretty good. And we start with k equals 1, which simply means we're going to start with the first y value. We're going to go to the nth 1, depending on how many we have. And instead of writing f of x sub 1, we just put f of x sub n, because it's however many we have, you add them up. And we divide that by n. So this is another way of writing, this is a short way of writing this whole thing over here. Just for humor me here, what I'm going to do next is I'm going to take this expression and I'm going to separate it. So I still have my sigma, no problems, it's just there. And what I'm going to do is just separate this into two pieces. So this is the same as f of x sub n times 1 over n. Okay? Now, here's where my setup earlier is going to come into play. You see this 1 over n? Remember we said 1 over n is delta x over b minus a? So what we're going to do is we're going to just take this 1 over n and we're going to replace that with delta x over b minus a. So my next step will be to take my summation notation, k equal to 1 and f of x sub n, that's still there. But instead of 1 over n, we're going to replace that with delta x over b minus a. Now, this b minus a, it's really just a constant. It's the difference between b and a. So it's always going to be some number. It's not going to depend on how many rectangles you have, because no matter how many rectangles you have, the distance from b to a is always the same. So I'm going to go ahead and pull it outside of the sigma notation. It's just not going to matter. As long as I add up those terms and multiply them by delta x, I can always multiply by 1 over b minus a, and that's going to give me the same exact answer as if I had left the b minus a here. So I'm going to go ahead and take it out. Okay, remember it's on the bottom, so the top, if I factor only the b minus a, there's a 1 on top. So there's my sigma, okay, sorry about that, sigma, k equals 1, and so what's left over inside is f of x sub n, and we're going to multiply that by delta x. Now this is how you find the average value of a function. You add up all the y values, if we were taking a specific number of them, multiply by the width of the interval and by the width of the rectangle, and then multiply by 1 over b minus a. This would be the formula. But this is just an approximation because we would be assuming that is a certain number of rectangles. We really want to have all the rectangles. We want all the y values, all the heights of those rectangles. So the way that we do that is there's an infinite number of them. There's an infinite number of y values here. So what we're going to do is we're going to go ahead and take the limit. This is still the same thing. But it's now going to be the limit as n goes to infinity. That way we have an infinite number of them. And if you're thinking, where have I seen this before? Where have I seen this before? Please, please, please think back a while back. This is the summation symbol. We have that. That means add f of x of n, the y values, times delta x. The limit as n goes to infinity. Well, this is nothing more than the integral. This was the integral in summation notation. And remember, as n goes to infinity, this summation notation becomes a sigma. The f of x of n, well, we don't have n anymore. We have an infinite. We have all of them. So we just need to write f of x. And the delta x becomes dx. And so we have to list our interval from a to b. And ladies and gentlemen, here it is. This is the formula. This is how you find the average value of a function. And I know it's kind of crazy because we're using integrals, but basically you take an integral of the function and you multiply it by 1 over the width of the interval. So all this long proof was to get this formula. This is what you have to memorize. This is what you have to know. Okay? So how does that help us with our problem that we were working on before? Let's go back to that guy. Whoops, too far. All right, so it says find the average temperature. Well, if we use the formula would say take 1 divided by the width of the interval. In this case, it would be 24 minus 0, so that would be 24. And the integral from 0 to 24. And you want to go ahead and take that of the function that you're working with, f of t, dt. Now, we're not going to do that by hand. Absolutely not. We'll do it with our handy-dandy calculator, which is right here. Let's go second quit. All right, so we don't want to do a derivative. We want to do an integral this time. Math 9. We're going to start at 0. We're going to go to 24. And instead of typing the function, it's a pretty long one, we're going to use vars. And then dx. Okay. Let's get an answer. So that's just the integral part, okay? Well, 1920, that doesn't make sense for the integral. But if you remember, that isn't the integral. That isn't the average, sorry. That number doesn't make sense for the average temperature. I mean, 1,920 degrees is not even here. So what we're missing is we actually have to multiply that by 1 over b minus a. So in other words, you have to divide by 24. Let's see what we get. 80. Whoops, sorry, I didn't mean to. 80 degrees. Now we had already guessed that, but here it is. Taking the integral and dividing by the width of the interval gives us the average value of the function. This is not a rate. This is literally the degrees on average that day took on, 80 degrees. Okay? Now we're not ready to answer the last question yet because we haven't done the mean value theorem. So let's go ahead and back to our, one second. I'm going to put pause on that one. And I'm going to show you, we're going to do another example. I think I gave this to you guys in class. Hopefully I did. I took the temperature yesterday from weather.com. This is just a snapshot or screenshot of the weather in Yuma from 9 p.m. to 3 a.m. And I went ahead and I just took the temperature. These are just the temperatures. And so it says find the average rate of change of the temperature between 9 p.m. and 3 a.m. Well, at 9 p.m. it was 81 degrees, so I'm going to go ahead and take that. Subtract the temperature at 3 a.m. At 3 a.m. it was 70 degrees. It's going to be 11, sorry. You didn't hear that. And then I want to make sure you understand, we're not going to do 3 minus 9 because we're going to get a negative answer. And if you notice, okay, I'm going to pause because I did that wrong. Let's erase. Yep, totally did that wrong. Here, let me redo. Remember, you want to take b minus a, f of b minus a, and I did f of a minus b. So actually what you want to do is 70, minus 81. So I know 9 is bigger than 3, but 3 a.m. is actually further in time, so that one should go first. And on the bottom, you don't really want to do 3 minus 9. And the reason is because technically 3 is before 9. So the way you think of this is 9, 10, 11, 12. This is actually 13, 14, 15. Okay? So you have to think of 3 a.m. as the 15th hour, basically. So we'll go 15 minus 9, and that'll do it. So it'll be negative 11 divided by 6. And negative 11 divided by 6 is negative 1.333. 1.83, repeating. And that, of course, is average rate of change of the temperature. So it's going to be degrees Fahrenheit. And the changes in time is in hours. It says make an educated guess about the average temperature in Yuma from 9 p.m. to 3 a.m. Well, as you can tell, the temperature is decreasing. That's why we got a negative rate. I'm going to guess, I don't know, 76, 75-ish. Let's just say 75 degrees. It says use a trapezoid approximation sum to approximate the average temperature in Yuma from 9 to 3 a.m. Well, if we're approximating the average temperature, we're going to use that same formula. The formula is 1 over b minus a. So in this case, it's going to be 15 minus 9. And it's going to be the integral from 9 to 15 of the temperature function. I'll just call it f of t again, dt. But here's the thing. With a table, there's no function. There's no function. So with a table, we can't use Math 9. We can't type in a function. We can't do antiderivative because we don't have a function. So what we're going to do is we're going to use a trapezoid approximation to approximate this piece. So this piece right here, we're going to use a trapezoid approximation to give us what this is supposed to be. And it's not going to be exact, it's not going to be perfect, but it's going to be close to what the answer should be. If you notice, right here, we'll be able to draw trapezoids that are 1 hour apart. So we'll be able to do 3, 4, 5. We'll be able to do 6 of them, okay? And they're all 1 hour apart, so I can use a formula. So my trapezoid approximation would be 1/2, and I'm using the formula because the width of the interval is the same. The height is 1, and I'm going to do the first y value, which is 81, plus 2 times the second, plus 2 times the third, plus 2 times the next one. And I'm going to press pause and finish this. You can do this. Okay, so here we are. I set up my trapezoid rule, and then I put it in my calculator, and I got 449.5. But don't forget, so this Riemann sum comes out to 449.5. This number is the approximation of that integral. Now, again, we were not able to find the integral because we have no function. So we're using a trapezoid approximation to come up with a number that gets close to this integral. So here we are, 449.5. We still have to multiply by 1 over 15 minus 9. So when we do that, we are actually dividing by 6. And the result comes out to 74.9167. And that would be degrees Fahrenheit. Because remember, this is actually temperature, the average. And I had guessed it was 75, pretty darn close, 74.9. So the last part of this video is going to talk, we already found average value. Average value, if you remember, we just did, oops, is this piece right here. And so now we're going to talk about the mean value theorem. And the mean value theorem says if a function is continuous on an interval a to b, then at some point the average value of the function will actually equal the y value. So this f of c represents a y value on f of x, on a function f of x. So again, this is saying that if you find the average value, at some point the function will take on that value. And here's an example algebraically. It says find the average value of x squared minus 1 and determine the point where f of x takes on the average value. So let's go ahead and set this up. The average value will be 1. Whoops, I didn't give you a interval. Just a second. Pause for just. It should be on 0 to 2. So I forgot that part. Find the average value of this function on the interval 0 to 2 and determine the point where f of x takes on its average value. So again, will be 1 over 2 minus 0, and we'll set up the integral from 0 to 2 of x squared minus 1 dx. And this should give us the average value. Okay, so you can go ahead and press pause for just a second and go ahead and calculate that integral. You can use your calculator. I guess you could do it by hand if you wanted to. So my calculator tells me that this comes out to 1/3 or 0.3 repeating. And so this is the average value. What the mean value theorem then says is that we can take the actual function, x squared minus 1, and we can just go ahead and set that to the average value, which is 1/3, and solve for x, and that'll tell us where the function will take on that value. Now keep in mind, when we get our answer, it should be inside the interval. So x squared will equal 1/3 plus 1, or plus 3 over 3. So we get that x squared equals 4/3. And we take the square root of both sides. We get a plus or minus, but again, we are only going to take care of the stuff in the interval. So x is just going to be positive. Technically 2 over square root of 3. And then that's it, we're done. And if you want to rationalize, I guess you can, which would be 2 square roots of 3 over 3. So once you find the average value using the formula we generated earlier, you just set the equation, the original, not derivative, original equation equal to that average value, and you do that, and you solve for x. So how does this go back to that last question at the beginning we sort of skipped over? It says, at what time during the day is the temperature the same as the average temperature? Well, the average temperature we found was 80. So now we have to find at what time of the day that temperature equals 80. So that would be this function. In other words, we got to set up this whole entire function equal to 80 degrees. So we have 80 minus 10 cosine of pi x, or t, over 12. And we got to set that equal to 80. Now, I'm not going to try to solve that by hand. That's just too complicated. So we're going to use a calculator. And here's what you're going to do. You're basically, we already have this function in y1, the temperature. This one's already in y1. So I'm going to think of y1 equals this whole thing. So we're going to think of 80 as y2. We're going to think of it as y2 equals 80. So we have two equations here. Y equals this long one, and y equals 80. Going to our calculator, y equals, we already have the temperature function set here. So now what we're going to do is just go ahead and enter y equals 80, because that's what we want to set it equal. And what you're going to notice when we graph this, oops, sorry. What you're going to notice when you graph this is that there's two places where the line y equals 80 and the f of t function, they meet up. And these points, this is where that temperature of 80 degrees, the function is equal to it. And we already know it's going to happen at 6 a.m., 6 p.m. But one of the ways you could also have your calculator find this is you just go to second, calc, and this time we're going to find intersect. is we want to figure out where those two functions intersect. It's going to ask you to tell it which is the first function, so we're going to use that temperature function. And then it's going to tell you to specify the second one, which is the 80. And then it's going to ask you to guess, and you see it's guessing because there's two possibilities here, so I want to just move closer to one of them so that the calculator knows which one I'm talking about. Okay, just a little bit closer, there you go. And then I'll just press enter, and it tells me that in fact the intersection is 680. So at time equals 6, we get one answer. And if you go repeat the process, you're going to get actually 18 because it's 6 a.m. and 6 p.m. So we go back to our question, and it's going to say, at what time does this happen? Well, we said 6 a.m. and it happens at 6 p.m. So average value, we have a formula. 1 over b minus a times the integral from a to b of the function. And the mean value theorem simply says, hey, once you apply that average value formula, whatever you get, set your function equal to it, solve for x or whatever variable you're using, and that's the place where that function is taking on the average value. And that's it. Hopefully this made sense and you're ready to practice.